Dear students, today we are going to discuss the numericals on chemical kinetics, considered to be one of the most important chapters for JEE preparation. Whether it's JEE mains or advanced, the questions that are asked from this chapter always have significant contribution to the entire paper. Minimum you can anticipate one question in JEE mains. When it comes to the advanced, the questions may be asked on the comprehensive based or math the following. I mean to say the weightage might be little more than the mains for the advanced in this chapter. Now the first problem is that we have a reaction process where A and B are reacting and the rate of the reaction is followed as such that it is first order with respect to A and second order with respect to B, and we have taken 1 mole each of A and B, which has been introduced into 1 liter vessel with the initial rate being 1 into 10 to the power minus 2 mole per liter per second. Then you have been asked to calculate the rate when half of the reactants have been converted into products. So you have got the reaction here clearly. Initially, the components that are present in the reaction vessel are 1 mole each. Initial, that is at 0 time. What I mean to say that when you have started the reaction, there were 1 mole each of A and B were present in 1 liter of vessel. Hence, you have got the concentration of these two initially, right? So when I have assumed the rate constant as some K, you know that the rate is equal to K. I mean to say rate constant into concentration raised to the power their orders. It is given that it is first order with respect to A and second order with respect to B. Hence, you will be writing the rate law first. Now, when you substitute the values over there, you will be seeing that the rate is given as 1 into 10 to the power minus 2 mole per liter per second, K into initially they were present as 1 each. I mean, from this data, you will be finding out the value of K, the rate constant. So, this is your initial situation. Then later, it has been given that half of the reactants have been converted into products. I mean to say the half mole had reacted over here. So, out of 1, if half has reacted, half are going to remain. And since they are reacting in 1:1 mole ratio, I can anticipate here the same half to react here also. So, the remaining is 1 minus 1 by 2. 1 is initial, 1 by 2 reacted. So, the remaining is 1 by 2 again, and 1 by 2 mole per liter of B is present. So, therefore, in this case the rate, here it is 1, here it is 2, but rate constant do not change, but the concentrations have changed, order do not change. What I mean to say, the final rate will be when you substitute the K, which is going to remain as constant as it is the rate constant. So, when you substitute here the values, you are going to get it as 1.25 into 10 to the power minus 3 mole per liter per second. This is the final rate of the reaction when half of the reactants had been converted into products. Now, the second question is, we have a first order reaction which is 20% complete in 10 minutes. Then you have been asked to find the rate constant for the reaction and also the time taken for the completion of 75% of reaction. So, over here, we have been given that it's a first order reaction. As far as first order reaction is concerned, the integrated rate law clearly suggests that K can be calculated by using this expression, where the rate constant is calculated at a stipulated time by using the initial and final concentration of the reactants. Now, it's given that 20% of the reaction is over in 10 minutes. What I mean to say, that when I have got the K for a first order reaction substituted in terms of the half-life period, as we all know that K can be calculated by using this K or T half of for a first order reaction is independent of the initial concentration. This is the relationship between these two, which is equal to 2.303 divided by the time course of this reaction is 10 minutes. Initially, if I assume as 100 mole of this substance or the reactant which is reacting, then we can see here clearly 20% of this 100 has gone. So, the remaining, that is 80, will be 80. Now, from this expression we will be finding out the T half, that is the half-life period of this reaction. Now, after finding out T half, we know that this is your K which you have got after such substitution. You know that This simplification will fetch you the value of K, which is the first question answer for you. The K is turning out to be 0.0223 minute inverse. This is the answer for your first question. Then after finding out K or T half from this relationship, we know that for a first order reaction, the time required for the 75% completion is 2 times of T half. So when I substitute here my T half value by using this expression, you have got T half as 0.693 divided by 0.0223. This many minute is the time required for the completion of 75% of the reaction, which is 62.18 minute. So you got both the answers. So the answer for this question is B. As you can see here clearly that we have calculated the value of K as well as the time required for the 75% of the completion of reaction. In the third question, we have 0.1 gram atom of a radioactive isotope with half-life period being 5 days. Then you have been asked to find the number of atoms which are decaying during the 11th day. So here, my dear students, we have this radioactivity reaction concerned question where you can see that radioactive isotope with atomic number Z and mass number A is decaying with a half-life period of 5 days. And you know, all radioactive decay follow first order kinetics. So based on this principle, what we are going to do is we are going to apply the integrated rate law for the decay of this radioactive isotope. Now here you had been asked to find the number of atoms that are decaying after or during the 11th day. That is, what I will do is initially I will be finding out the number of nuclides or atoms that are remaining after 10 days. And I will also find out the number of atoms that are remaining after 11 days. Now when I subtract the number of atoms that are remain after 10th day and after 11th day, I will be getting the number of atoms that are decayed during the 11th day. What I mean to say that we have the number of atoms remaining after n number of half-lives is equal to the initial number of nuclides into 1/2 whole power number of half-lives. So this is we know that we are going to use this simple formula to find the number of nuclides that are remaining after n number of half-lives. So I am going to find out the number of nuclides remaining after 10 days, which is equal to initial nuclides, which is given to us 0.1 gram atom. I mean to say 0.1 mole or 0.1 into Avogadro number many atoms have been taken initially. Number of half-lives. Now you can see that for every 5 days there is one half-life, and here we are talking about the situation after 10 days. For every 5 days, if it is representing one half-life, after 10 days it will become how many half-lives? 2 half-lives, right? Similarly, you have to find out the number of nuclides remaining after 11 days, which is equal to initial number of nuclides into 1/2 whole power number of half-lives. That for every 5 days it is one half-life, for every 11 day it will be 11/5 many half-lives. Now you have got the number of nuclides remaining after 10 as well as 11 days. So therefore, number of nuclides decayed during 11th day equal to N10 minus N11. That is now simplification of this will give you the number of nuclides that are decayed during the 11th day, and the answer for this question is C. That is 1.95 into 10 to the power 21 atoms of this radioactive isotope have decayed during the 11th day. We have 10 gram atoms of an alpha active radioisotope which are disintegrating in a sealed container. In 1 hour, helium gas collected at STP is 11.2 liter. Then you have been asked to calculate the half-life of the radioactive isotope. So here you see we have got one radioactive isotope, say X, with the atomic number Z and mass number A, undergoing the decay in a sealed container where helium gas is evolved. That is the combination of the alpha particle with the free electron we call as helium gas. And when helium gas is evolved or alpha particles are evolved, the resultant daughter nuclide will change its atomic as well as mass number. Now you have been given that you have taken 10 gram atom, I mean to say 10 mole of radioactive isotope initially, and after t seconds or after 1 hour you have been asked to find the what you call half-life period of half-life period of this particular isotope when you are given the volume of the helium gas which is collected after 1 hour. Now it is clearly mentioned that the volume of helium gas collected at STP is 11.2 liter. At STP we know how to find the number of moles of helium. We divide that with 22.4, which is nothing but the molar volume. Now it is turning out to be half mole of helium is formed during the decay after exactly 1 hour. So after 1 hour of time, half mole of helium gas is formed. Now we know that they are reacting in 1:1 mole ratio. Hence, for every half mole formation of helium, half mole of X might have reacted. Hence, the remaining moles of this will be 9.5 gram atom or 9.5 mole. Now, you know, for a first order radioactive decay, lambda, I mean to say the decay constant, which is equal to 0.693 by T half, because you have been asked to find the T half, is equal to 2.303 divided by time taken for this process. If you are getting your answer in hours, please do not change the time, which is given as 1 logarithm of initial mole of the radioactive isotope divided by final moles. Now simplification of this simple equation by substituting the log values which will be given to you in the numerical questions will fetch you the T half value ultimately, and the answer for this question is D, with T half is equal to 13.51 hours. Now in the fifth question we have a first order reaction for which the graph is plotted against log K and 1 by T. We have a straight line with a slope of minus 6000 is obtained, and you have been asked to find the activation energy on the basis of this data. Now we know this question is related to the Arrhenius equation with the K being equal to this much, where you define each and every term this as the rate constant which indicates the number of fruitful collisions, whereas A is called frequency factor or collision factor, which indicates the total number of collisions. This is fruitful collision, these are the total number of collisions. Hence the ratio will fetch you the fraction of molecules that are participating in the fruitful collision is called as Boltzmann factor. Now we know this A, and we know that activation energy, and this is universal gas constant along with the temperature. Now to get the prescribed information to be used by using this equation, let us apply the logarithm to this, where log base E is being used in order to eliminate the exponential factor, and when I convert this into the log with base having 10, I am going to get this ultimate expression. And when this expression is compared to that of y equal to mx plus c, you will see that there is a negative slope. What I mean to say, that when I wish to plot a graph between log k versus 1 by t, you know that I am getting a straight line with a negative slope and slope being equal to So the value is provided to us is minus 6000. When I substitute here, the EA can be obtained. Now depending upon the units of R, you are going to get the value of EA. Now if I wish to calculate this in kilocalorie, I will be substituting the R as 2 into 10 power minus 3, and the answer for this question after such substitution is B, that is 27.6 kilocalorie. We have a drop of solution whose volume is 0.05 ml, which contains 3 into 10 to the power minus 6 mole of H plus. If the rate constant of disappearance of H plus is 1 into 10 to the power 7 mole per liter per second, it is asked to find how long would it take for H plus ion drop to disappear. So in this question, please do not use any kinetic equation in order to solve this. You can get the answer by looking at the units of K. What I mean to say, that you have been given the value of K for the disappearance of this H plus containing drop as 1 into 10 to the power 7 mole per liter per second. This information clearly indicate that if your drop, which is containing H plus ion, has this much concentration, disappear in 1 second. So if your such drop, which is having that much of H plus ion, is disappearing in 1 second, we have here one drop which is having the concentration which is equal to 3 into 10 to the power minus 6 mole of H plus present per 0.05 milliliter. I am taking here, I am getting this many moles are given, and when I am substituting here 0.05 milliliter, I am going to convert into liter by dividing it with 1000. You know that this ion drop, H plus ion drop, disappear in how much time? Then you have been asked to find the time which is required to disappear the H plus drop which is having this much concentration. After simplification, you will be getting the time required for the drop to disappear after such substitution as 6 into 10 to the power minus 9 second. That is the answer for this question is A. We have a first order reaction with K equal to 1.5 into 10 to the power minus 6 second inverse at 200 degrees Celsius. If the reaction is allowed to run for 10 hours, what percentage of the initial concentration would have changed into the product? And you have been also asked to find the half-life of the reaction. Now since it's a first order reaction, you have the equation where you will be calculating the value of K by using the integrated rate law. Now since the percentages are dealt or asked, we can rewrite this equation as K 0.693 by T half. I am taking the base 10 and the initial concentration as 100, and the remaining will be 100 minus X if number of moles or concentration of A reacted is being assumed as X, then the remaining will be 100 minus X. So what I mean to say that the final concentration here from these expressions, as you have seen in the previous case, is equal to the initial concentration into 1 by 2 whole power number of half-lives. Either we can use this relationship or this relationship depending upon the requirement. Now you can see here the first question is to find the percentage of initial concentration that would have been changed into the products, that is the number of moles of the reactant or percentage of the reactant which has reacted. So better we go for this, since we have been provided with the K and you have been also provided with the time, running time of the reaction, and also this will fetch you the value of T half. What I mean to say, this time when I use this expression, you know that K, which is equal to 0.693 by T half, is equal to 1.5 into 10 to the power minus 6 second inverse. This is given to us. Now T half will be when I substitute that value is this many second. I am going to say 4.6 into 10 to the power 5 second approximately. This is the T half what has been asked to you as a part of this question. And next, when you know T half or the value of K, when you substitute here, as we know that the reaction is allowed to run for 1 hour, because this is given in second inverse, you have to convert the time in second. 1 hour means 3600 second, and when you substitute here all the values, you have to get the X, which is happened to be for this question is 5.26%. So this combination is there in option C, hence the answer for this question is C. We have the next question where the decomposition of N2O into N2 and O2 in presence of argon follows second order kinetics, and you have been provided with the K as 5 into 10 to the power 11 into exponential of minus 29,000 K by T, and you have been asked to find the activation energy of this reaction. Now you know this question is based on the Arrhenius equation, where I will map the information given with this. You can see from the data, it's clearly indicative that A is this many collisions are taking place in 1 second per unit volume is nothing but the definition of this A. And when you map these two, you know that minus EA by RT is equal to minus 29,000 K by T. Here, dear students, don't get confused with this K, as we are aware of the fact that T gets cancelled. This K is nothing but the unit of T, which is being written as T by K, or upwards K as the numerator. So K is not a Boltzmann constant or rate constant or any equilibrium constant. It is just the unit of this temperature, which has to be written like this. When you write it like this, it go as the numerator. At times the excess information or confusing data will be provided to us. So as I told you, depending upon the units of this R, you are going to get your answer. This time I am going to take R as a 8.314 into 10 to the power minus 3 kilojoule. So when I substitute this in kilojoule per mole, I am going to get my answer. I mean to say, when I substitute here the value, the answer for this question is 241 kilojoule per mole. That is option A is correct for the given question. In Arrhenius equation for a certain reaction, we have been provided with the values of EA and A, which are 98.6 kilojoule and 4 into 10 to the power 13 second inverse respectively. If the reaction is of first order, at what temperature will its half-life period be 10 minutes? So once again the question is on Arrhenius equation, where K you would be writing as this much. The solution to this question once again is linked to the Arrhenius equation, where you are provided with the values of the activation energy and the collision factor. Then it is also given that it is first order reaction, and you have been asked to find the temperature at which the half-life period be 10 minutes. Now what I am going to do is I am going to substitute here K, because it is a first order reaction. K can be substituted with 0.693 by T half. The half-life period for this reaction is given as 10 minutes, which I am going to convert into seconds because the other factors are in per second. Now this is your K. Now the value of A is provided to you. The value of A is 4 into 10 to the power 13 collisions are taking place per second into exponential of minus the activation energy for this question is 98.6 kilojoule. Then when this is being taken in kilojoule, the value of R also should be in kilojoule. and you have been asked to find the temperature at which this whole thing is taking place. In all such cases, we will be using the logarithm. I mean to say, when you write log of 0.693 divided by 600 is equal to log of 4 into 10 to the power 13 minus 98.6 divided by 8.314 into 10 to the power minus 3 into t into 2.303, because I have converted here also the log base e into the log base 10. Hence, I am dividing here the entire equation with 2.303, which I am getting like this. Now, when I simplify this equation, I will be finding the temperature at which half-life for this first order reaction was found to be 5 minutes as 311.35 Kelvin. That is option C. Now, in this question, we have azomethane decomposing, and you have been given the half-life period for the azomethane as 30 minutes. Then the first question is to find the fraction of azomethane that will be decomposed in 1.5 hour, and also the time for 60% completion of the decomposition of azomethane. Now, the point is that it is following the first order kinetics. We will take the reaction here. Azomethane is undergoing the homolytic fission when it is being heated, giving rise to ethane as well as N2 gas. Now, this is being a first order reaction. You know that the fraction of azomethane that will be decomposed has to be calculated in a stipulated time. Then I will be using the first order kinetics for this reaction, that is K, which is equal to 0.693 divided by the half-life period for this azomethane is given in minute, that is 30 minutes. K is equal to 0.693 by T half is equal to 2.303 divided by the running time of this reaction was found to be 1.5 hour. This is given in minutes, hence I will be converting that into a minute as well. So, this many minute into log of the initial I will assume as 100 and the reacted if I assume, or the decomposed if I assume as x, the remaining will be 100 minus x. Now, simplification of this will fetch us the answer for the first equation, that is percentage of azomethane decomposed is nothing but x, whose value is found to be 87.4%. If you have substituted this as 1, you will get that as 0.874. Then after that, you have been also asked to find the time at which 60% of the decomposition is complete. What I mean to say, that the half-life remains the same because K is constant. Then you have to find out the time at which 60% of the reaction is over. So, if you assume initial as 100, the remaining is 40 because 60% has gone. So, here you will be getting the time in a minute after simplifying this expression as 39.7. So, therefore, answer for this question is option A, where 0.874 is the degree of dissociation and the time required for the completion of 60% of the reaction is approximately 40 minutes. In a particular reaction, the time required to complete half of the reaction was found to increase 16 times, whereas the initial concentration of the reactant was reduced to 1/4. What is the order of the reaction? Now, this question is based on the relationship between the half-life period for a given reaction, let us assume as T half, and initial concentration of the reactant which is undergoing the change is A naught square bracket. At times this could also be the partial pressure. Now, we all know that from the integrated rate law, this is always, these two are linked up by using this expression. Now, it is given in this question that the time required for the completion of half of the reaction, that is nothing but the half-life period, is increased by 16 times when the initial concentration was reduced to 1/4. Now, when I assume that the initial half-life period is T1 and initial concentration of the reactant is A1, it said that the half-life period is increased 16 times. I mean to say it has become 16 times of T1 when the initial concentration of the reactant is reduced to 1/4. What I mean to say that A1 has become A1 by 4 whole power n minus 1. Now, when I take the ratio of the two, you can see that T1 upon 16 T1 is equal to A1 by 4 whole power or divided by A1 whole power n minus 1. So, you can see, my dear student, that there is a relationship between T half and initial concentration, which I am writing here. I have assumed that the initial concentration when it is A1, the half-life period is T1, and it has become 16 T1 when the initial concentration is reduced to 1/4. Now, when I am taking this ratio, I will be applying the logarithm. Here T1 and A1 gets cancelled. When I apply log here, log of 1 by 16 is equal to n minus 1 times of log of 1 by 4. So, what I mean to say that this equation upon simplification will fetch you the value of n, which is nothing but the order of the particular reaction. So, the answer for this question is option A, as you get n equal to 3.